Before I do that, start the recording. Yes, thank you. I know that. Okay. Okay. Use substitution. This is your very first technique of integration. Okay, can everybody see my screen and hear me?
Yes, ma'am.
Okay, good. Yeah, and what you're doing with use substitution is sort of using the chain rule backwards, because the derivative of a composition of two functions, so f of g of x, is f prime of x times f prime. Okay, the derivative of composition f of g of x is f prime of g of x times g prime of x. So the inside function here is g of x, outside function is f. But if the derivative works that way, the antiderivative works the other way. And that's supposed to be an x. Okay, and what you're going to be doing when you use this little technique is trying to see this pattern, that you have a function inside another function and you have the derivative of that function sitting in the integral for you. Not divided, but multiplied. Okay. All right, so kind of a shorthand way of thinking about it. We'll let u equal to g of x, that's the inside function. So du dx is g prime of x, or du is g prime of x dx, and then the integral, okay, becomes, so this integral f of u, it's also f of g of x times g prime of x. Okay. This, remember, g is u, and g prime of x dx is du. So these three things are the same. Yeah, and capital F is just any antiderivative of little f. Okay, so we looked at this, we looked at some problems on Wednesday, but here's an example where it's perfectly set up for a use substitution. You've got x squared plus 1, and that whole thing's being squared. And then you've got the derivative of x squared plus 1 sitting there for you, okay? That 2x dx. So here, it would work very nicely if you let u equal to x squared plus 1. So du is 2x dx. And that changes the integral to integral of u squared du. And okay, what's happened here is you sort of absorbed, you've absorbed that inside function. And it makes, when you go from here to here, this one looks a lot easier to do, because it is. Okay, but you've not thrown away g of x or u. You haven't thrown it away. It's still all there. It's just sort of absorbed into this u, and it makes the overall picture easier to handle. Okay, so any derivative of u squared, that's just u cubed over 3 plus a constant. And then you want to go back to the original variable, which was x. So antiderivative is x squared plus 1 cubed over 3 plus c. Any questions? Okay, I'll take that as a no, although it'd be nice. Is my microphone still on?
Yes, ma'am, it is.
Okay, good, good. Just checking. Okay, let me just change this a little bit. That 2 right there, I don't really need to have that in there. It's a constant, and you can adjust for constants. You cannot adjust for the lack of an x, okay? So let's just look at a slightly modified problem. If I had x squared plus 1 squared x dx, well, the derivative of x squared plus 1 is 2x dx, and I don't have that 2. But that 2 is easy to put in and take out. This is equal to, okay, there's one way to look at it. Well, I'll make it 2x, and I put a 1/2 out front. Remember, constants that are multiplied by a function can come in and out of the integral. They can come in and out. Nothing else can. But that 2 and 1/2, certainly. 1/2 times 2 is x. Okay. So u again, x squared plus 1 du 2x dx. The integral becomes, still have that 1/2 out front, 1/2 u squared du and 1/2 u cubed over 3 plus c, which is 1/6 u cubed plus c, and then put back in your x's, 1/6 x squared plus 1 cubed plus c. Okay, so constants, you can modify things so that constants are taken care of. Let's try another one. I'm getting these examples out of your book. Your book's got a ton of problems. Okay, sine squared of 3x times the cosine of 3x. dx. Okay. So I've got the sine of 3x all squared. The derivative of the sine of 3x, okay, that 3 on the outside is not a problem. U substitution works very well here too. Yeah, what I'm noticing, I've got this sine function, which is really, that sine of 3x is inside the squaring process, but I've almost got the derivative of the sine of 3x sitting there for me. So let u be the sine of 3x, then du, okay, it's the cosine of 3x times 3, because of chain rule, that 3x in there. 3x is an inside function too. Okay. There's du. And okay, I have cosine of 3x dx in my integral, but I can take care of that. 1/3 du then is cosine of 3x dx. So, okay, let's come down here. Okay, so cosine of 3x dx gets replaced by 1/3 du. And sine of 3x is u, so that's just u squared. And notice I convert all of my x's over to u's. Now, some people like to do it one step at a time, and that's fine with me. But you cannot integrate until you have all x's or all u's. You don't want x's and u's mixed together. And the 1/3 can come out. It's a constant. And then we have 1/3 u cubed over 3. Okay, so that's 1/9. And what was u? Sine of 3x. Okay, and you can also, of course, write that as okay, commonly done. Okay, any questions?
No, ma'am.
Okay, let's see. Let me find some good problems here. Oh, let's do one. Okay, that's a definite integral. And I'm going to go through two ways to work it. Okay. If it's a definite integral, you can, if you change your endpoints from the original ones in terms of x to whatever the new ones are in terms of you don't have to go back to x before you evaluate. For indefinite, it's nice to get your final answer in terms of your original variable. Okay, so here, let's see. Here's one. The integral from 1 to 2 of 2x squared times the square root of x cubed plus 1. Okay, well, here, I think a u substitution will definitely help because the derivative of x cubed plus 1, well, it's 3x squared, okay? 3x squared instead of 2x squared. But that the 2, 3 thing, we can easily adapt for that. So I'm going to let u equal to, So du. And 1/3 du is x squared dx. Okay. So way number one. I am going to stop that.
That's good.
Yeah.
Can I just ask, the way that we're getting that 1/3 in front of du, is that just dividing both sides by 3?
Yes, it is.
All right, cool.
Okay, so here's my original problem. And okay, so that 2, I'm going to pull that 2 out. Okay, before, I don't know where that red line came from, but whatever. Okay, 2 times the integral from 1 to 2 of x squared times the square root of x cubed plus 1 dx. Okay, now I can make my substitutions. X squared dx is equal to 1/3 du. I'm leaving the endpoints off for the moment because I've got to be careful. Yeah, so x squared dx gets replaced by that, 1/3 du. And that square root becomes the square root of u, because u is x cubed plus 1. Now, my endpoints changed. When I changed my variable, my endpoints changed. When you look at this, okay, if this says I'm integrating over the interval, x's are all between 1 and 2. Well, the u's aren't. So if let's see, 1 is less than or equal to x cubed is less than or equal to 2 cubed. And then adding 1 to all 3 sides. Okay. So my u endpoints, and x cubed is u, are 2 and 9 instead of 1 and 2. Okay. 2 and 9. And then, let's see. All right. So I'm going to bring that 1/3 out. And then I've got, okay, somebody needs in. U to the 1/2 du, and that gives me 2/3. The antiderivative would be u to the 3/2 over 3/2. You want to go from 2 to 9. And let's see, that's going to be 2/3 times 2/3 is 4/9. Simplifying that complex fraction there. And then u to the 3/2 from 2 up to 9. And since I changed my endpoints to be in terms of u, I don't need to go back to x here. Okay, so 9 to the 3/2 minus 4/9, 2 to the 3/2. And let's see, so square root of 9 is 3. And 3 cubed is 27. And then the square root of 2, well, that's nothing good. It's just square root of 2 cubed. That's going to be 4/9 times 2 times the square root of 2, right? Okay, so let's see, what's the best way? Well, you could leave it like this. Or you could, okay, so that I could write it at that number is 12 minus 8 times the square root of 2 over 9. Yeah, leaving it in this form is okay with me. These are all numbers as far as I'm concerned. Okay. So that's way number 1, where you change your endpoints over 2. Now, if you don't want to do that, okay, what I usually do, okay, let's write down the problem again so that I'll have it in front of me. I just forget momentarily that it's a definite integral, and I get the indefinite integral. The problem with this is sometimes you forget to go back, okay, and evaluate it, get a number. But okay, so basically I'll look for the antiderivative first, and of course it's the same process as before. U is x cubed plus 1. Du is 3x squared. 3x squared dx. So the integral becomes, and 1/3 du is x squared dx. So you get 2, and I'm going to go ahead and bring that 1/3 out. And then it's the square root of u du. So 2/3 antiderivative of u to the 1/2, which is 2/3 u to the 3/2 over 3/2 plus c, which is 4/9 u to the 3/2 plus c. But u is x cubed plus 1. So I'm going back to my x's. Okay. And there's my antiderivative. In fact, the whole family of them. Okay, but I'm not finished because my original problem was not an indefinite integral. It was a definite integral. But now I have an antiderivative in terms of x. So the integral from 1 to 2 okay, here's my antiderivative. And it gets evaluated from 1 to 2. And notice I never went to the u endpoints because I just went for finding the indefinite and the antiderivative first, okay? And I got that back in terms of x. So I'm back to my original endpoints. Okay, and that's 4/9, and then 2 cubed plus 1 would be 9 to the 3/2 minus 4/9 times 1 plus 1 would be 2 to the 3 halves. And that's the same thing as we got before. Right there. Okay. Same answer. And that, of course, if they're both correct, they should be the same. Any questions?
No, ma'am.
Okay, good. Let's see. Let me throw one out here. What about this problem? Do you see any u and derivative of u sitting there for you? Well, I don't. Okay. And I threw this in because not every problem is going to be workable with the u substitution. Not every problem. U substitution is a tool that you can pull out and use when it's appropriate. It is not always appropriate. I don't see anything I could put in here for u that would, and then have u prime sitting in there for me. Okay. But I don't need a u substitution to do this problem. What do I need to do?
You could just believe it's factor in the right into two.
Yeah. Yeah. I'm going to expand. Okay. So multiply it out. And okay, so I need to multiply x cubed times 1 is x cubed. X cubed times x to the minus 3 is 1, right? Minus 3 plus 3 is 0. Then x times 1 is 1. And x times x to the minus 3 is x to the minus 2. There'll never be a rule that tells you how to handle the integral of a function times a function. Never, 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 unfortunately. You got to get around it somehow. Okay. Trying to integrate, well, in this case, you can. And now instead of having it written as a product, I have it written as a sum. And when it's written as a sum, I can divide it up into the sum of integrals. And now it's easy. Okay, so this is just x to the 4th over 4 plus x squared over 2 plus x to the minus 1 over minus 1 plus c. Okay. Any questions? One thing you want to keep in mind For differentiation, we got this whole list of rules, okay? We could handle sums, products, quotients, compositions, integration, which is the inverse process of differentiation, is not nearly as straightforward. It's more of an art form. You're going to have to look at an integral, figure out what your function is doing, and what you see, what patterns do you see? Can you change the form of the function? What can you do? It's not going to be so obvious as to how to proceed.
Dr. Kennedy,
Yeah.
that next step you did, in the problem with last problem, did you use x to the n+1 over n+1?
Yes, I did. Yes, I did.
Okay. All right, just making sure. So we just used FOIL and then just added the intervals together.
Yeah, this goes back to the properties of integrals. Okay, we had this property that if you had the sum of two functions, that means you can break it up into the sum of two integrals. First of all, to break this one integral up into the sum of four integrals. And now everything is basically using the rule x to the n. Okay, as long as n is not equal to -1. But tomorrow we're going to start about talking about this when n is equal to -1. But yeah, on this one, and this one, I use this rule. And for one, well, we also had the rule that the antiderivative of a constant was the constant times x. So it's 1 times x. Yeah, I'm using the properties of integrals here, and that's all.
All right, thank you.
When you're doing a U substitution, you're going a little bit beyond just the properties of integral. Okay, I have one picked out here. Okay, here a U substitution works fine, but it's a little bit harder to see what U should be. Because it's a little bit harder to see that U prime is in there for you. Okay, would somebody take a wild stab at what U should be?
I would assume it would be 1 plus the square root of x.
I think that's a good choice. Okay. And why does that work? Well, let's see. Du then is 1/2 x to the -1/2 dx. And okay, that's equal to 1/2 times the square root of x dx. And you've got 1/2 the square root of x dx in your integral. The 2, not a problem, because you can bring it in and out. In fact, let's see, let's just go ahead and take care of it here. If I multiply both sides by 2, I'll have 2 du is 1/2 the square root of x dx. And that's looking good. Okay, everything's going to match up. So is going to be, okay, I'm going to pull the 2 out, that 2, and then I've got du. Remember, du is all of this. So all that's left is 1 over u squared. And this is a lot easier to evaluate than this is, right? That was the whole point of using this technique, to make your problem easier. And I can go ahead and evaluate. So that's u to the minus 2. That's 2u to the minus 1 over minus 1 plus c. And that's minus 2, 1 over u plus c. What was u? 1 plus the square root of x. So it's minus 2 over 1 plus the square root of x plus c. Questions? Okay, I'm going to up the ante a little bit. Where was that problem? That must have been later. Your book actually has several sections on this. I think this one will do. Okay. This one. Well, okay, what makes this a little bit hard to deal with? If you got that square root of 2x minus 1 in the denominator, okay, and I can't break it up into the square root of 2x minus the square root of 1. That violates all kinds of algebra rules. But yeah, the fact that I've got not just an x under that square root makes this problem look a little difficult. And it's not so obvious that a u substitution would work. Okay, because x dx, well, but I think it will. What the u substitution is going to do is let me shift the complicated stuff out from under the radical. So I'm going to let u equal to 2x minus 1. Now, will this work or won't it? Okay. You don't always know in advance. And especially you don't know in advance if you're just learning how to do this. You're not always going to make the right choice. I don't always make the right choice, even though I've been doing this forever. But if you don't make the right one to start with, try something else. Okay, so I'm going to try this. Oh, stop that. Du then is 2 dx. because the derivative u prime is just 2, right? Well, all right. So that's going to get me this changed over, and with, I take 1/2 out, I've got dx changed over to u's, but I've got to change the x over too. Well, let's see. U is 2x minus 1, so u plus 1 is 2x, and u plus 1 over 2 is x. So I can change that x over to u's also. So now this is equal to, okay, the dx gets replaced by 1/2 du, and I'm going to pull the 1/2 out. It's a constant. I'm allowed to do that. 1 over the square root now becomes 1 over the square root of u, and I've got to replace that x. It's u plus 1 over 2. So everything has been replaced. All my x's are now written in terms of u. And let's see if this helps. Okay. Well, I've got another 1/2 in there, right there. I can pull that out. And then I've got u plus 1 over the square root of u. And that is u plus 1 times u to the minus 1/2. And that is u to the plus 1/2 plus u to the minus 1/2. U times u to the minus 1/2 is u to the 1 times u to the minus 1/2. 1 minus 1/2 is 1/2. So that's where that plus 1/2 comes from. So I just expanded here. Okay. But now it's easy, right? This is easy to evaluate, just using the x to the n thing. That looked a little bit daunting. Now it's easy. Okay, 1/2 plus 1 is 3/2 divided by 3/2 plus 1/4 u to the plus 1/2 over 1/2. So that's 1/4 times 2/3. Uh, 1/4 times 2. And 1/4 times 2/3 is 1/6. And let's see, what was u? The square root. Oh, u is 2x minus 1. And 1/4 times 2 is 1/2. Any questions on that one?
Could you go back down?
Yes. Is that where you wanted me to go?
Yes, ma'am. Thank you.
Okay. Okay, and I do, well, absolutely great that you are trying to understand as we go, because that's the only way to do it. But I do post the notes every day. They actually look nicer after the update that I complained so much about. So they do go up. Of course, after they're posted, I've got all these things I went back to and circled and whatever. And so maybe that's a little distracting. Okay, let's see, where are we? Maybe time for one more. How about this? Okay, I'm changing this one a little bit. Just to let you know, okay, if I changed it to something that's harder than I thought it was going to be, it's because, yeah, basically all the problems in your book are somewhat rigged to be doable. And it's easy to change one a little bit and have it be completely not doable. But okay, here we go. Let's see what we can do. This is sort of like the previous one. I think a U substitution is going to allow us to shift the complicated part out of the square root, okay, and into the polynomial part, which will make it easier to deal with. So I'm going to try this. I'm going to try u equal to x plus 4. If I do that, then du is dx. And okay, so I've taken care of, got that in terms of u, that in terms of u, got to get that in terms of u too. Well, let's see, x is u minus 4, right? That's what that says. So 2x is 2 times u minus 4, and 2x plus 1 is 2 times u minus 4 plus 1. Or I could expand that. That's 2u minus 8 plus 1 is 2u minus 7. All right, so I've got 2x plus 1 then switched over to u's also. So this integral becomes the 2x plus 1 is now 2u minus 7. Square root of x plus 4 is the square root of u, and dx is du. So it's switched over to u's. Okay, so let's see. U to the first times u to the 1/2 is u to the 3/2. And then minus 7 u to the 1/2. Okay, so, well, break it up one more time. You get to where you're doing a lot of this stuff in your head, okay? And after you get some experience and are very comfortable with certain of the properties. Okay, 3/2 plus 1 is 5/2. 1 half plus 1 is 3 halves. So that's 2 times 2/5 minus 7 times 2/3. And that is 4/5. Okay, and what was U? U is x plus 4. And there we have an antiderivative. So it worked out fine. Yeah, so sometimes you can use a U substitution in this way to get the troublesome part out of a denominator or out of a radical or something like that and move it out so it's basically in a polynomial and it's easy to evaluate. Any questions? Okay, tomorrow I'm going to start talking about that, which we've avoided. This is the n equal to minus 1. Okay, and the x to the n, remember we keep saying this is x to the n plus 1 over n plus 1 for n not equal to minus 1. Because if you try to do this, you get x to the 0 over 0, which is meaningless. But this one, okay, a very important integral. And we are going to talk about it in terms of the fundamental theorem of calculus and develop all the properties. Okay, so stick around if you have questions. Otherwise, we'll call it a day.
Have a good day.
You too. Dan,